Welcome to today's explainer, everyone. I am so excited you're here because today we are going to learn exactly how computers think and solve problems. You know, it might sound like absolute magic, but by the end of this lesson, you'll be writing your very own instructions just like a real computer programmer. Okay, let's dive right into this. So, I want you to think about something you do every single day. How do you pack your school bag perfectly every single time? Well, you probably check your timetable, find the right books, tuck them into your bag, zip it all up, and leave it by the door. Without even realizing it, you're using an invisible set of sequential steps to solve a problem. You, my friend, are basically functioning like a highly advanced computer.
Here is our game plan for today's masterclass. We'll start with everyday problem solving, then figure out what algorithms actually are, and look at computer programs and logic. After that, we'll learn flowchart symbols, build our very own simple flowcharts, and finally, wrap up with a quick chapter review and quiz.
All right, let's kick things off with our first topic, everyday problem solving. We're going to see exactly how human problem solving builds the foundation for machine logic. Imagine your mom asks you to go grab a pack of bread and butter from the grocery store. If someone asks how you'll do this, you might just shrug and say, well, by going to the shop. But wait a second, is that a complete answer? Think about it. What if you get there and realize you have absolutely no money? Or what if you totally forget what you were supposed to buy? What if you leave your change on the counter? See, just saying go to the shop sounds easy, but a real, actual solution needs a proper series of activities performed step by step.
And that brings us perfectly to our next section, where we learn the official technical term for this kind of organized step-by-step thinking.
So, here is the absolute crucial takeaway. An algorithm is a step-by-step procedure of solving a logical or mathematical problem by dividing it into proper sequential steps. Now, I know that definition might sound a little complex, but it's actually super simple. An algorithm is always written straight to the point, just using simple English. It's literally just a list of instructions in the correct order.
Let's look at how we turn that grocery store trip into a proper algorithm. Step 1. Take money from your mother. Step 2. Go to the shop. Step 3. Ask for the grocery items. Step 4. Pay the money. Step 5. Collect your items and the remaining amount, if there's change. And finally, Step 6. Return to your home. Notice how we didn't skip a single detail? Everything is in a completely logical sequence. I mean, if you tried to pay the money before you took it from your mom, it definitely wouldn't work, right? All right, now it's your turn to be the algorithm designer. We have a scrambled after-school routine here. Your mission is to rearrange these steps into the correct chronological, meaning time-based order. The steps are play football with friends, go to bed, change uniform, check diary and complete homework, and have dinner. Take a second, honestly, hit pause on this explainer if you need to, and figure out the most logical sequence. Okay, how did you do? Here is the correct logical sequence. First, obviously, you change your uniform so it doesn't get dirty. Then, you play football with your friends. After that, you check your school diary and knock out that homework. Next, you have dinner. And finally, you go to bed. If you nailed that, fantastic job. You are literally already thinking like a programmer. Now that we've totally mastered human routines, let's jump into our next section and see how computers follow instructions. Because, believe it or not, unlike you, computers actually can't think for themselves.
A computer functions in a step-by-step manner too, but it can only solve a problem when it knows the exact proper instructions. A computer cannot work on its own. It needs help. These instructions are created by a user, someone exactly like you. We call this a computer program. It's simply a set of step-by-step instructions given to a computer to do a particular task, and it uses those exact same algorithms we just learned about.
This brilliantly illustrates how we write a mathematical algorithm for a computer. Let's say we want to find the sum of two numbers. Notice something really special about Step 1 and Step 6? Step 1 is start, and Step 6 is stop. A computer algorithm must explicitly tell the machine exactly when to wake up and begin, and exactly when it's totally finished. In between all that, it reads the first number, reads the second number, adds them together, and prints the result for us to see.
Let's look at a slightly trickier puzzle. Ava wants to find the greatest of three different numbers, let's call them x, y, and z. She starts and reads the three numbers. But look at Step 3. It says, if x is greater than y, this introduces what we call if-then decision-making. The algorithm is basically asking the computer a question. Based on the answer, it jumps to different steps to compare the winner against Z. This is exactly how algorithms handle complex, changing conditions.
Okay, we have done a lot of reading. Now that we can write algorithms in text, let's move on and learn how to draw them visually. Welcome to the world of flowcharts.
The easiest way to think about this is that an algorithm and a flowchart are basically just two sides of the exact same coin. Side 1 is the algorithm. That's step-by-step text written in simple English. Side 2 is the flowchart. A flowchart is a type of diagram that represents an algorithm visually. Instead of just words, it uses different shapes to represent different actions. There are 6 basic symbols you really need to know. Let's knock out the first 3. First up is the terminal box. Pay close attention to its shape. It is an oval. This oval is used exclusively for the start and stop commands at the very beginning and end of your program. Next is the input-output box, which is a parallelogram. A rectangle with slanted sides. We use this parallelogram whenever we are feeding information in or getting an answer out. Third is the processing box. This one is just a standard rectangle. The rectangle indicates an action, like dicing a mango, or doing math, like addition.
All right, now for the final 3 symbols. The decision box is shaped like a diamond. We use this whenever we need to raise a true, false, or yes, no question, just like that if-then logic we saw with Ava comparing those 3 numbers. Next, we have flow lines, which are simply arrows. They connect all our symbols together and show the exact direction the program is flowing. And finally, connectors, which are small circles. If your flowchart is getting super long and has to break to another page, you just use a little circle to connect them up.
Let's move right into our next section and see how all this builds into something amazing. We're going to combine our algorithm text with our brand new visual symbols to build a real flowchart.
Imagine we're making a delicious mango shake. First, we use an oval terminal box for start. Then we need our ingredients, right? So taking the blender, mango, and milk goes into a parallelogram because that is our input. Next, we dice the mango. That's an action, so it goes in a rectangle processing box. Turning on the blender is also an action, so another rectangle. Pouring the fresh shake into a glass is our final result, our output, so we go back to the parallelogram. And finally, an oval to stop. Notice how the arrows always point downward? A simple flowchart almost always moves in the vertical direction, from top to bottom.
Now let's translate our earlier math algorithm into a flowchart. It's so simple. Oval for start, parallelograms to read A and read B because we are inputting those numbers. A rectangle for the action of adding them together, sum equals A plus B. A parallelogram to print sum because that's our output, and an oval to stop. See how cleanly the text translates into these visual shapes? It makes complex programming so much easier to read at a single glance.
Wow, we have covered so much incredible ground today. Let's lock in everything we learned with a rapid-fire revision and a final quiz to test out your new programming brain. Okay, rapid-fire recap time. Remember, problem-solving requires sequential steps. An algorithm is that step-by-step procedure written in simple English. A computer program is when we give those exact instructions to a computer. A flowchart is simply the visual diagram of that algorithm. The general flow direction is always top to bottom or sometimes left to right. And our core shapes are the oval for start-stop, parallelogram for input-output, rectangle for processing, diamond for decisions, arrows for flow, and circles to connect. And now for your final question to take away with you today. If you wanted a computer program to check if a specific number is even or odd, which flowchart shape would you use to ask that question? Think about it. You're asking a yes or no question, right? Like, is it divisible by 2? Which means you need to make a decision. That's right, you would use the diamond shape. You guys have been absolutely amazing today. You now know the secrets of how computers think and how to visually map out literally any problem in the world. Keep practicing your algorithms, and I will see you in the next explainer.